Thank you very much, Kelly, for your introduction. In this talk, we will describe two families describing the population dynamics inside a chemostat. This work has been made in collaboration with Pablo Amster from Buenos Aires, Daniel Sepúlveda from Santiago de Chile, and Frédéric Massange and Silvio Julian Niculescu from Paris. The first section makes a brief description of a chemostat, while the second section shows the differential equations describing the chemostat operation. In particular, the second section explains what is the competitive exclusion, which is an important topic in theoretical ecology. Next, we explain how delays can help us to provide a better description of the above-mentioned chemostat processes. Next, we will show how we can avoid the competitive exclusion by constructing a chain of chemostats. And finally, we introduce a model of delayed chemostat with periodic inputs. Now I want to explain briefly what is a chemostat. The chemostat is a continuous bioreactor with constant volume developed in 1950 by Aaron Novick and Leo Slizard. Its operating parameters allow to reproduce the essential features of simple microbial ecosystems, namely a spatially homogeneous and possibly time-varying environment. In addition, a supply of nutrient is introduced in order to be consumed by the microbial species. We have a vessel with a liquid medium. As you can see, we have inputs and outputs. The chemostat contains a limiting nutrient and one, and possibly more than one, microbial species which consume and compete by this nutrient. This input is only an input of nutrients at rate D with concentration S in, and the output contains a mixture of nutrients and microbial biomass, also with rate D. This helix means that the liquid medium is well starred. More information and more details about the mathematical modeling of chemostat can be found in these works. I especially like the first monography of Hall-Smith and Paul Waldman. These more recent works are also quite interesting. Now I want to describe briefly the differential equations of the chemostat. The variable S will denote the concentration of nutrient. The variable X denotes the concentration of microbial biomass. This equation describes the evolution of the nutrient. You can see that this term describes the input of nutrient. This term describes the output of nutrient. The second equation is the per capita growth of the microbial biomass, and this term describes the output of microbial biomass. We have to describe two processes: the consumption of nutrient by the microbial biomass and the growth of the microbial biomass. In this framework, we will assume the following fact: that the consumption of nutrient is proportional to the biomass growth. We can see that this term describes the consumption of nutrient, which is almost similar to the growth of biomass. The unique difference is this constant of proportionality. This term is a function, mu. We will call it the growth function, and we will assume two properties. Fixed point at 0, we will assume that this function is differentiable and the derivative is positive. The most iconic example is the Monod function, and you can see this expression. We also can consider two or even more microbial species in competition for the same nutrient as follows. And in this talk, we will assume the existence of two constants, lambda1 and lambda2, such that this identity is satisfied and this inequality is satisfied. In order to understand what are these constants lambda, you can see this identity, the growth function is equal to D. In this graph, the red curve is the growth function, and this line is the constant D. The intersection is reached at this point lambda. Also, let us recall that this equation can be seen as follows, since mu evaluated at lambda is equal to D. You can see if the nutrient concentration is bigger than lambda, the derivative is positive, which means that the microbial biomass is increasing. On the other hand, if the nutrient concentration is lower than lambda, you can see that the derivative is negative, so the microbial biomass is decreasing. In this context, the constant lambda is named the break-even concentration for a microbial species, which is the minimal amount of nutrient ensuring the growth of the biomass. Having in mind what is the break-even concentration, I want to explain the competitive exclusion principle in a chemostat context. If this inequality is satisfied, then any solution of the competitive chemostat has this asymptotic behavior. We can see that the nutrient concentration is convergent to this break-even concentration. The first species in competition will be driven to extinction, and the second species in competition is convergent to this positive constant. You can see that the species related to the lower break-even concentration will be the unique survival in this competition for a nutrient. This result is known as the competitive exclusion principle, and in this case is adapted to the chemostat. Mathematical proofs can be found in this reference, and a more general reference is the work of Butler and Volkovich. I have to say that the competitive exclusion is a general principle in theoretical ecology and has been experimentally verified in chemostats. In order to explain how we can consider delays in chemostat equations, the idea is the following. We can consider a delay between the process of consumption of nutrient and its effects on the biomass growth. The first model has been proposed by Caperon, which consider here the consumption and here the growth. There exists a delay between the two processes. A second model has been introduced by Ellermeyer in 1991 and proposed this relation between the consumption of nutrient and the growth of the biomass as follows. We can consider the competition between two species for a nutrient by considering the Caperon idea for delay, and the competitive exclusion has verified in this reference. But also, we can consider the competition between two species for a nutrient by using the Ellermeyer approach. And for the Ellermeyer case, there exists several references explaining how we can obtain the competitive exclusion. Our idea will be to assume that what can we do to promote the coexistence between two species if the competitive exclusion is verified. And I want to show the first result, which has been made in collaboration with Frédéric Massanque and Silviu Iulian Niculescu in this work. we will consider a delayed chemostat in the Capron sense with two species in competition for a nutrient. We will assume that the competitive exclusion is verified. So we will assume that in this vessel, we have the competitive cultivate the disadvantaged competitor in a separate chemostat. The first two equations describes is the concentration of the disadvantaged competitor in the first chemostat. Of the disadvantaged competitor in the second chemostat. The variable XA is the concentration of the advantaged competitor in the second chemostat, and is1 and is2 will be the concentration of nutrient in the first and in the second chemostat, respectively. We also assume that the growth functions mu1 and mu2 are of this type, which we have seen that this the monod function. In addition, we will assume that the break-even concentrations, lambda1 and lambda2, are such that the following inequality is satisfied. If we assume this inequality, we can prove the existence of a unique positive equilibrium, and we can see the components here. It is easy to verify that the first four components are positive. This inequality implies that this coordinate is also positive. So originally, we have competitive exclusion. If we prove that this equilibrium is globally asymptotically stable, we have avoided the competitive exclusion, and we have promoted the coexistence between two species in competition. This is our main result, which provides sufficient conditions ensuring the global stability of this equilibrium star. The first assumption is an explicit bound for the delay, stated here, and the second inequality is an implicit bound for the delay. I said implicit because you can see some terms in red, and these terms are dependent of delay. For example, S and T, you can see that are terms which depends on delay. Now I will show a very a sketch of the proof. First, I will consider the first chemostat equation, which can be transformed in this new equation by using this transformation. In addition, we will make this translation. You can see that this term and this term are the first two coordinates of the equilibrium E star. With this translation, this system becomes this new system, and the unique equilibrium is the origin. And our idea will be find conditions ensuring the global asymptotical stability for the origin. To do that, we will construct this Lyapunov-like function where this term is described here and this term C1 is described here. This is the work with respect to the first two equations. Now we will focus our attention in the last three equations. As before, we will introduce three transformations, this one, and this one, and the above transformations transform these three equations in this equation. also, as before, we make this translation. You can see that this term, and this term are the last three coordinates of the equilibrium E star, and this system is transformed in this system. We also can see that the origin is the unique equilibrium of this system, and our idea will be proved that the origin is globally asymptotically stable. And to do that, we will construct this Lyapunov function. So we have this Lyapunov function related to the last three equations, and we have this Lyapunov function related to the first two equations. Now we will take the derivatives along the trajectories, and we can verify the existence of two constants, C0 and C1, such that the derivative along the solutions satisfy this inequality. I will not show the computations to arrive to this inequality. This is the most technical and hard to follow part of the article, but the tools are several integral inequalities as Cauchy-Schwarz, Young inequality, Jensen inequality, and several estimations in the spirit of techniques developed by Frédéric Massange in several publications for bioreactors, but also in theoretical works involving Lyapunov functions. If we have this inequality, we will integrate here. And now we have to recall some fact. The solutions of the chemostat equations are bounded. So these two functions are bounded, and this will imply that this integral is convergent. Moreover, we can prove that the solutions are uniformly continuous, and we can apply the Barbalat lemma, which will imply that this function, and this function are convergent to zero when t tends to infinite. We have to recall that these three functions are translations from coordinates of the equilibrium. So we have this convergence, and this convergence. And the last two limits are a technical exercise, but it's quite easy if you read the article. So we can see that the solution of the chemostat equation are convergent to the equilibrium E star, and the theorem follows. Summarizing, the idea of help the disadvantaged competitor under this restriction will imply the coexistence of two species in competition in the form of a stable equilibrium. If this inequality is not verified, then the previously advantaged competitor will be driven to extinction, and the previously disadvantaged competitor will be the unique survivor. We expect to extend this result by considering delays in the Euler-Meyer cells, because we have only considered the Caperon case. I also want to say that we can extend these results considering a third species in competition, and the case in absence of delays has been studied by Guillermo Contreras on his master thesis. Well, this is the first result that I wanted to show. The second one is about a chemostat equation with delays and periodic inputs. And this work has been made in collaboration with Pablo Amster and Daniel Sepúlveda. We will consider this chemostat. The delay is described by following the approach of Caperon, and the novelty is that we are considering a periodic input of nutrient. In order to explain the novelty of this model, I want to make a short revision of the previous literature. There exist several results considering delay, but constant input of nutrient. The first two works are essentially local stability analysis, and the last three are global stability analysis, considering several functions. A second family of results consider no delays, but periodic inputs of nutrient. The first work is a numerical analysis made by Su. The other ones are proof of global stability of a periodic solution. Nevertheless, surprisingly, there exists no results considering delays and periodic inputs of nutrients. Our work can be seen as a contribution in this sense. In order to show our main result, we will consider the particular but important case where this initial condition is equal to 0. In this case, this system becomes this ordinary differential equation, and we can verify that this function, b star, is solution of this equation. Moreover, we can prove that it's periodic with period omega, and also that it's a globally attractive solution for any solution of this equation. This function, we will call it as washout solution, and will play a key role in our main result. This is our main result. We have the washout solution, we have the growth function. The composition of the growth function with the washout solution is a periodic function. This integral is the average of this composition. And if this average is bigger than D, it can be proved that this system has at least a positive omega periodic solution. So our result is a result of existence of periodic solutions. And I will show a sketch of the proof. We have the system, and we will introduce this notation. This coordinate of the initial condition with this constant gamma. This system can be transformed in this integral differential equation, and we can construct a Poincaré operator to this equation. We will make a restriction for this Poincaré operator to this set where the initial condition C, phi, is bounded by 0 and by the washout solution. By using the Chowder fixed point, we can prove that this Poincaré operator has a fixed point. Now we will introduce this set C, where for each L we have a fixed point of the Poincaré operator, and we will make a union with the fixed point and 0. For each fixed L, we will consider the fiber associated to this set, and we will construct a map F, where is phi is solution of this integral differential equation with this initial condition. Now, it will be important to see this equation. So we can see that if S and X is a solution with this initial condition, we can see that X evaluated at T plus omega minus xt is equal to this integral, which is equal to this function. So this coordinated will be periodic if and only if this function is 0. On the other hand, note that this initial condition satisfies this property. So we have periodic solutions here and periodic solutions here. So the existence of omega periodic solutions for the chemostat equations is equivalent to find a couple of initial conditions at this set C such that this function is equal to 0. So if we want to obtain the existence of periodic solutions, we have to find roots for this equation. The idea can be seen as a generalization of the Bolzano's theorem, namely to prove that F is continuous and has a change of sign on a connected subset of C. The continuity of F can be proved easily by using theorems of continuous dependence with respect to initial conditions for the system. In order to study the change of sign, we have to recall this assumption, which implies this inequality. So, as F is continuous, we can find functions close to phi star and LO close to 0, such that this inequality is verified. We also can prove that if L1 is big enough, we can find also a phi1 such that we have the opposite sign for F. Now, we have that F is a continuous function. We find a couple of initial conditions satisfying this inequality, but we also find another couple of initial conditions satisfying a reverse inequality. This is for smaller values of LO, and this is for bigger values of L1. Now we will define a compact subset of this space, K, which will be the union of fibers with L going from LO to L1. This is the most technical part of the article. By using Weiburn lemma combined with the Leray-Chowdhury degree, we can prove the existence of a connect component of K connecting the fiber associated to LO with the fiber associated with L1. Then we will have a root of this function. In consequence, the existence of this root will imply the existence of a Merca periodic solution for our model of chemostat with delay and periodic inputs. This is only a result of existence, and these results can be seen as a partial generalization of this result of Gail-Volkovich and Kiao-Qiang Chao. You can see that the equation is almost the same, but without delays, but the assumption is the same with respect to the washout solution. In absence of delay, they have a result of existence, uniqueness, and attractiveness of a periodic solution. We have working trying to obtain uniqueness and attractiveness results. We have a partial success for uniqueness in this result. We have the same assumption concerning the average. And if we consider delays small enough, we can prove that our model has a unique positive omega periodic solution. The tools for this proof are the implicit function theorem and Fredholm alternative. We have no results for attractiveness. We are thinking about how to do, but we expect to use this result in order to study these two periodic models. As you can see, they are periodic models for competition. This is a periodic model with competition in the Caperon sense, and this is a periodic model of competition from an Eller-Meyer approach. We think that the previous results will help us to study these two works. Now, with this last slide, I finish my presentation, but I want to acknowledge the Matansud program, which is the cooperation program between France and South America. And last but not least, I want to acknowledge the session organizers for their kind invitations. I am very glad to be here. Thank you very much.